Now it says it's recording. Okay, it looked like it actually was recording earlier too, but okay. So we have this data set which we have seen before. So we have some alcohol-related variables. We have this grouping of drinkers, and let's do something here real quick. Let's go analyze descriptives, explore, and we are okay. We're just going to explore drinkers for right now, just so we can see how many people are in each one of these groups. I probably should have tabbed that, right? Yeah. Analyze descriptives. Is crosstabs how we actually get people in groups? No? That's frequent. Oh, yes, thank you. Analyze descriptives, frequencies, and then move drinkers over and just hit OK. And actually, I'm going to come over to variable view here. Oh, wait. Well, that's fine for right now. All right, so when we look at frequencies, we have 4 groups of drinkers. Well, 4 groups of students. One group are people that do not drink, so that is our 0 group here. And then we have these 3 other groups of people who drink a little bit, people who drink a little bit more, and people who drink an awful lot, right? And if we wanted to examine the differences across these groups, how would we do that? Let's say we want to look at differences in urgency across groups. How would we look at differences in urgency across groups? Yes. I'm sorry, I'm just changing all of these right now. Okay. If we wanted to compare those values across groups, so how would we do it? If we wanted to look at... We can do that, and we will get to that. You guys spend a whole semester doing this. How do we compare groups? Just, we can do a simple ANOVA here, right? And everything that we're going to be doing today, it's basically the same thing that can be done within ANOVA. Next week, we'll talk about why we're doing coding rather than ANOVA, because it becomes important next week when we want to look at differences and associations across conditions, which you can't do in ANOVA. But for both regression and ANOVA, coding works exactly the same. So we can go analyze, compare means, or general linear model. Let's go compare means, one-way ANOVA. And if we want to look at differences in urgency across these groups, we would put urgency over here. We would put drinker in as our factor, right? This making sense so far? Is this how you guys did one-way ANOVAs last semester? Or did you guys use the univariate option?
We did the way.
Either way? Okay. We can do contrasts. You can come in here and look at the different contrasts, or we can do post hoc tests. And so let's just check a Bonferroni post hoc test. Or if you want to assume that variances are unequal, you could do that. And we hit go. We see that we have an F of 14.092. That is a statistically significant difference across groups. Of course, you can't tell where that difference is until you come down here and you look at this, and it shows you here are your mean differences across groups comparing each one of these. And this winds up being equivalent to what you would get if you did this in regression. Let's go back and let's go analyze univariate, because I think you can get effect sizes if you use univariate, right? Let's do fixed factor and put urgency back over here. And options, we want to get estimates of effect size. We're going to display means for overall and for drinkers. Compare main effects. And we will do Bonferroni just like we did before. And of course, univariate allows you to get quite a bit more information than what you get from the other piece of this, right? Our partial eta squared for our groups is 0.026, and F 14.092, that's what we had before, right, up here, 14.092. And again, we can compare these kind of group differences just like we did before. This is the exact same thing as the ANOVA that we had listed before. The interesting thing here is you have your sets of means, right? It will give you your sets of means, and then it tells you the difference between these means, and it really is just the difference between, so for example, between 0 and let's do 3. The difference is 0.192, and if you look up here, you can subtract these out, and you will get 0.192, and you do get a significance test of this, right, which is 0.05. Anyway, this is, since it's urgency, it's actually kind of interesting, right? What we see here is that the non-drinkers have fairly high levels of impulsivity. Urgency is impulsivity, right? And then, but obviously the heavier drinkers have the highest levels of impulsivity. Anyway, let's do something else now. We've talked a little bit about this in the past. If we have a group or a variable with a bunch of groups in it, and we want to break that group into variables that we can use in regression instead of ANOVA, what do? What's our, okay, so we can start with dummy coding, right? So let's start with dummy coding. If we have our groups here that are labeled as 0, 1, 2, 3, how are we going to, and we assume that 0 are non-drinkers, how are we going to code this? G minus 1, right? We need 3 dummy-coded groups. What are the 3 dummy-coded groups going to be? Okay, we can call them 1, 2, and 3. And group 1 is going to have what for values? Say that again. 0 and 1, where are the ones going to be? Anyone who has a group 1, and then it'll be 0 for everything else, right? Group 2, similar. You'll have 1 for everyone who's in group 2, and then 0 for everything else. And then for group 3, we will have 1 for everything that's in group 3, 0 for everything else. Let's do those. Let's create those. So we go transform, compute. We're going to call this group 1. Oops. And we're going to say equals 1 if drinker equals 1, right? Does this work if I do it like this? Does it have to be equals equals, or is it just equals? Actually, let's do something else because I am not sure that that's going to work.
It's called recode variables. So go to analyze, transform, and recode variables.
Ah, that's how we do it.
Or
Yes.
If you compute variable, you can just hit drinker equals 1 and it will pop out.
Say that again.
If you go to compute variable and you do the new name and then drinker equals 1,
Yeah.
it will pop out ones for all the ones and zeros for the rest.
It will put zeros for the rest?
I just did it.
Okay, so let's try this. So you said group 1, drinker equals 1. That's it? That's all I got to do?
Right. Yeah, it worked when I did it.
It worked when I did it too. You see there? All right. So there's group 1. Let's make those, let's do the same for group 2. Drinker equals 2. Transform compute. Group 3. Drinker equals 3. Oops, I screwed that up. Oh no, I didn't. That looks right. Transform compute. And we're going to call this group 0. Drinker equals 0. That's all you have to do? Huh. That is super simple.
Well, it doesn't work on Macs that way.
It doesn't? Because I'm using a Mac.
But are you using the ECF apps?
I am.
I have SPSS.
So
Okay, I know how to do it otherwise.
SPSS on Mac, it's not working?
Yeah, it says it's like an illegal character.
It says, what's an illegal character? My guess is that's something else. Now is it working on Mac?
Now,
All right.
of course, it's always the
Okay, so now that we've created these, if we want to test this, what do we do? Plug 3 of them into a regression model. So let's do that. Let's go analyze regression linear. We were looking at urgency, right? Let's put urgency in here. And let's go group 1, group 2, and group 3. Okay. And statistics. No. Let's just go with that. Okay. And here is our regression model. We see that we have an R squared of 0.026, F of 14.092, statistically significant, blah, 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 blah. Just want to scroll up here real quick and find my ANOVA table. And we see F of 14.092. And notice that in the situation where we have just grouping variables, where we're regression and ANOVA, and the only predictors that are in there are conditions, our eta squared, partial eta squared, is the exact same thing as R squared, right? So we have 0.026 is our eta squared here. If we come back down to our regression equation, our R squared is 0.026. And then we get our actual regression coefficients. And I'm going to point this out. It's important to put your regression coefficients in your write-up of your results. A lot of you guys put that there was a significant effect, and then you just put a p-value, or sometimes you don't even put that, in your homework. So in your homework, you should say like, there was a significant effect of blah, 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 and then you would put in parentheses B, whatever that B is, right? B indicates slope, and then comma, P equals, or P is less than, or whatever. Because this slope allows us to understand the kind of magnitude of effect of whatever we're talking about. And in this case, the magnitude of effect is a magnitude of effect on what? Say that again.
No drink.
It's a magnitude of effect relative to no drinkers, right? So when we're looking at our coefficient table right here, we have constant group 1, group 2, group 3. And then we have the significance levels of group 1, group 2, group 3, t-values, and so on and so forth. What does that table actually tell us? Okay, so let's start with, what is the intercept telling us?
The value of 0, like when there is group 0, its urgency is equivalent to 1.98.
Okay, so in group 0, urgency is 1.978, right? That's what you're saying?
Yeah.
Let's check that. Let's go data, select cases if drinker equals 0. Do I have to put equals? No. Equals 0. Okay. And now let's go analyze, descriptives, explore, get rid of drinker, and let's just put urgency in here. And this should give us our average level of urgency, and it is 1.9775. The standard error of 0.04935. 1.978 rounds it up, right? We don't need to see that. So anyway, yes, that is exactly right. That's what that intercept is. It's the mean level of urgency in the 0 group. Perfect. What is this coefficient then? For group 1, it gives us a slope coefficient of minus 0.113. What is that telling us?
So compared to the control group, group 1 has
Okay. Anyone have a calculator out? I can grab mine. 1.978 minus 0.113. 1.865, right? So let's go. So 1.865 should be what? The mean for people in group 1? Let's test that. Data, select cases, if drinker equals 1, okay. Analyze, descriptives, explore, don't have to change anything there. 1.865, I had 5. Right. So we're right? That's correct. This is exactly what it's supposed to be. Back to our regression table. So this slope is saying that there is a difference in intercept, right, between the control group, or the 0 group, always 0 group, and group 1, and that difference is 0.113, right? So based on that slope, you can figure out what the mean or the intercept is for group 1. What else can we get from this? What does this tell us?
It is the ratio of it is the ratio of so basically
That is actually the standard error of the difference between those two, right? And that's how you calculate a t-test for this. So we then have a t-value right here, and we have a p-value. What does this tell us? What do these two things tell us? The t-test and the p-value for that slope tell us what?
that there is a significant difference between the mean of the two groups.
Perfect. Let's do something here. Let's go data, select cases if drinker is less than 2. Okay. And now let's go analyze, compare means, one sample t-test. Oh wait, not one sample t-test. Analyze, compare means. Is it paired samples t-test? Is that right? Somebody's gonna have to help me out here because I am not good with this. Independent samples t-test. Ah, thank you. Okay, we are going to put drinker here, right? Find groups. Group 1, 0. Group 2, 1, 1. Everything look right so far? Okay. We hit go. Our mean difference between these two is 0.11273. That sounds an awful lot like what? That was our slope before, right? Except it was minus 0.11273. Why is our p-value different here than it was up here? We have 0.019, but up here our p-value is not 0.019, it's 0.039. What's going on there? No, no, no. In this example, these values control for the fact that there is actually not an n of, this is assuming an n of what? 554. Our regression model up here is assuming an n of, I don't know, 700 or 800, whatever, however many are actually in this, right? Because it's using the full sample. And so while your differences will be exactly the same, it actually is comparing this to the full sample rather than just a reduced sample. So when you subtract those out, the coefficient doesn't change, but you do get slightly different standard errors and slightly different t-tests and p-values because this is using the entire sample rather than a reduced sample. But the point of the difference is still there, right? Yeah, go ahead.
Could it technically go from significant to non-significant?
Yeah, sure. It could go from significant to non-significant because we're looking at something that's reduced. But this highlights an important point, which is that when you are doing this in ANOVA, you wind up running multiple tests followed by post hoc t-tests. When you do this all in regression, it happens all simultaneously, and you don't have to do those corrected p-values anymore, right? The p-values are corrected based on the fact that multiple tests are unnecessary, and it's already using the entire sample. So, all right. From this table, we can get everything that we need relative to everything else in here, right? What is the difference between group 2 and group 3? Can we figure that out from this table? How do we figure out? This was actually part of the exam, right? I had given you guys some stuff. How do we figure out what the difference is between group 2 and group 3 here? Not necessarily.
You can just take the difference there. What's the difference from group 2 to group 3? Then you know the beta coefficient, but you don't know whether or not that's significant necessarily.
Okay, so how do we do this? You're right. We don't know if it's significant necessarily just yet. How do we figure out what the difference is between group 2 and group 3? What can we do? You said take the difference of what?
Of the
Let's take this into steps. Let's break this down into steps. If we're going to break this down into steps, what do we need to do first?
So we'll go to as 0. We'll go to as 0. And so we decode and we rerun it, and then we can check whether it's significant or not with respect to the group 0.
Yes, so
But
we
can check there is a difference.
there we go. How do we figure out if there's a difference? How do we figure out what the difference is between 2 and 3? Yeah, we can go back and recode for
We can
sure.
add those two, like 0.192 minus 0.048.
that's a 2 plus.
So with reference to 0, 2 is 0.192 above. With reference to 0, 3 is 0.04 it back. So the distance between 2 and 3 will be the addition.
There we go. Yep. Do you guys understand that? So figure it out for me quick. How do we do this? Can somebody grab their calculator and figure this out? Let's see here. What's the intercept in group 2 going to be?
The difference should be 2.4.
Should be 2.4?
Yeah.
0.2.
0.24?
0.24.
There we go.
Yeah.
Yep, 0.24. Yep, so the difference is 0.24. And what is the, I mean, you can actually kind of, if you look there and you had to guess of a slope coefficient of 0.24, is that going to be a significant slope coefficient?
Yes, because 0.19 is already significant.
Yeah,
So
it's going to be bigger than any other slope coefficient in the table, right? So you can guess that it's going to be. Is it possible to calculate whether or not or what the slope coefficient will be for that. Or the p-value for that, I'm sorry. It's not. I'm just going to tell you.
Yeah.
But if you look at those standard errors, you can see that across those standard errors, right, we're assuming roughly equal distribution of variance, right? And so across those standard errors, we've got 0.043, 0.055, 0.049, 0.057. We can guess that our standard error is going to be somewhere around 0.05, right? And that's going to be a significant t-value. But back to the original question is, if we test this, how do we test it then? You can just flip-flop these codings around, right? So if we wanted to test 2 against 3, then we would go analyze, regression, linear, and how do we change, what do we change in here?
What's included in the regression?
Okay, so which one should we drop out of here?
1.
Okay, are you sure?
2 or 3.
2 or 3. Let's drop 3 out, and if we drop 3 out, then we have to add something in, right?
0.
Add 0 in. We rerun this. What should our slope be for group? Did we drop 2 or 3 out? We dropped 3 out, right? What should our slope be for group 2? What the heck?
I think you have to unselect.
Oh, thank you. Data select cases, all cases. Now, analyze regression linear. What should our slope be for group 2? Before I scroll down, it should be what? What's that? 0.24. Yep. Let's scroll down, or negative 0.24 in this case, yeah. Because our control group now becomes the heaviest drinkers, right? Which we also know have the most impulsivity in this, so the most urgency. All right, with simple contrast coding, you can flip these around as much as you want. And you can have a look at a test of each one of these. It's not a multiple test because it's always the same model, right? Every time, every one of these is included in the exact same thing. So our f is never going to change. Our eta squared is never going to change. All of that stuff remains consistent. Here's our r squared or eta squared, whatever you want to call it. We can do an ANOVA in regression using coding, and we don't have to do the post hoc tests afterwards. We can see plainly from our original table what the differences are and test whether those differences are statistically significant, and it's not running an additional test, right? Okay, let's take a short break, and when we come back, we will look at weighted versus unweighted coding. Are there any questions before we take a short break? No? All right, cool. Short break.